To discuss topics that we presented today. So before going to discussion, so we can have some time to ask more questions to individual talks, because for some talks, actually we didn't have much time to finish all the Q&As. So therefore I am sharing my screen. Wait a moment. Okay, so I hope you can see my one slide. So this is a really quick, brief summary of all the talks that we had in this session. We had so many talks this time, so therefore I'm sorry if I'm missing some talks. So at the beginning, so Professor Tendoka provided a really comprehensive talk about the multi-messenger, multi-wavelength counterpart. Also, he included the future radio telescope and future X-ray telescopes, which will be really useful to identify FRB origins. Clancy James also really excellent talk, summarizing many topics, including the host galaxies. He briefly mentioned cosmology, but this cosmology, I would say personally cosmology using FRB is really important. And also he provided details about the population models of non-repeating and repeating FRBs. Sonjin provided the empirical relation, which is also could be related to cosmology. Jasper and Oliver and Leah, they provided the machine learning classifications. This also will be useful to identify, the physical mechanisms of FRB emission. Shibani provided a really good overview about the host galaxies, which again is useful to identify, constrain FRB origins. Also, I would say this is also important for future cosmology using fast radio bursts. Julian talked about the molecular gas property, which is really new in FRB host galaxy. That provide a relation between FRB and magnetar bursts, and then he strongly constrained all rate of the magnetar rate. And then Kosas also presented the possible upper limit on the sub-millimeter counterpart of FRB, which could be also useful to constrain FRB models. And then by looking at this, so maybe we can spend some time to ask further questions for individual talk during this discussion time. So if you have any remaining questions or comments, please raise your hand.
Yeah, actually, unfortunately, the invited speakers, they have some time constraints, so they can't remain here anymore today, but they are happy to talk on Slack. So maybe this kind of question could be raised for Slack, that we have still some presenters here. Yeah.
Okay, thank you very much for your support. Yes. Still, we can ask for some questions for the other, yes. For example, online talks. So if you have. Class is here? Okay. So is there any question or comments? Okay, Saha, please. Thank you.
Hi, I have a question for Clancy. I'm very curious to know how FRB would be very useful to constrain H0, because there were different astrophysical sources that are used to constrain H0, also including the GW and sometimes the kilonova. So what difference would FRB add to that context? I'm just curious to know.
Okay, so yeah, thanks for noting I just joined. So I guess there's two ways to compare FRBs. One are either to gravitational wave events, which are also new ways of probing H0, but also to the traditional methods, right, which are well established. So the clear advantage over gravitational waves is that we'll get there more accurately and sooner, because there's a lot more FRBs that are being localized at large distances than there are gravitational waves. So that's a fairly obvious answer. The counterpart to that is that gravitational waves are affected by less systematics. So probably in 100 years' time, gravitational waves will be doing much better than fast radio bursts. But I would be extremely surprised if in the next 10 years, gravitational wave cosmology has a significant competition to FRBs. Maybe 20-year timescale, if you look at detectors. If you compare it to the other methods, so for instance, supernova 1A and Planck, really the way to think of FRBs is that they need to assume something about the baryonic density of the universe, right? So they need cosmic microwave background constraints that relate H0 to omega B, because they don't independently measure omega B as well as H0. So what you basically have to do, and the way to think of this, is to say, okay, let's assume CMB measurement, right? Let's assume that is correct. Let's use those parameters, and then try to apply it to the nearby universe, the redshift 1-ish or less universe, which is what's probed by supernova. And then, if you find a value of H0 that's consistent with Planck, great. If you find a value of H0 that's inconsistent and instead is consistent with something else, then it might be that your value of H0 is correct. Or it might be something else in the CMB model is incorrect. For instance, if omega B was incorrect. So I think that's the way to think of FRB cosmology, if that answers your question.
Yeah, sure. Thank you very much for the answer.
Hello, actually I have a follow-up questions regarding this FRB cosmology to Clancy. Thank you very much for your nice talk. So yeah, I totally agree that the FRB will provide us the kind of independent constraint on H0, which is really important in future, I believe. But in terms of number of sample, so currently, we are only have say 20 FRB host galaxies, which is kind of limited. So then in future, so in order to achieve, for example, uncertainty on H0 measured from FRBs as small as say other competitive cosmological probes, for example, other methods. So how many sample for FRBs do you need to collect in future?
The answer is about, I'm trying to remember what it was, 200, I think, or thereabouts.
200 sounds possible. Okay, sorry.
Yeah, 200, 300 or so. It depends. So we did this study as part of our paper constraining H0, and I forget the exact result. I think it's 200. It might be 400. I think it's 200. And at that point, your random error comes down to about 0.1. Sorry, 1 kilometer per second per megaparsec or less.
Yes.
It's just that at that point, that's comparable to these various other systematics, and that's why I'm so keen to get together this group to try to reduce the other systematics, because we need to tackle them now.
Thank you very much, Clancy. That's a really exciting news. 200 sounds like possible in near future. So yeah, I hope the FRB can be really useful in future in terms of cosmology.
Yes. Yeah, it's convincing the optical telescopes to give us the time. That will be the challenge. The radio side will be fine. It's the 8-meter class telescopes and also James Webb as well. We need to get the
yes. I see. Thank you very much.
I also have a kind of question to Clancy. Thank you for a nice talk. As I remember correctly, you show result on the limit of the constraints on the index of the repeating rate, right? Using the previously known time repeating sources, about maybe 18 or 19. And as we see in today's many talks, we have now new sample from time, especially repeating one. So I wonder how this new sample will narrow down the peak position in your figure, constraining some index, for example, index in your analysis.
Yes, so what I'm worried about is that we're soon going to be faced by uncertainties in the modelling and the total population. So if you saw in one of my plots constraining that index, the difference between different population models was comparable to the uncertainty within each one. Now Chime have basically doubled the number of repeaters. You'll get square root of 2 reduction in error at a guess, and I think we need to reduce the population, reduce the uncertainties in the population models. So to do that, it's going to require modelling fast observations and probably DSA observations, because once you have telescopes with very different parameters at different frequencies, at different thresholds, that gives you a big constraint. The problem is the code at the moment, it's not slow, it's just that even without repeating parameters, you have to model 10 to the 7 simulations. And I think it's getting to the point where, because you have to estimate the effects of repeating FRBs to determine the reduction in low Z bursts, right? So if in the very nearby universe, if there's a lot of repeaters, you get limited not by the expected number of bursts, but by whether or not a bright burst happens to be in your cosmic neighbourhood. So it means that we're going to have to start fitting these 3 repeating parameters simultaneously with all the other parameters we fit, which will mean going from 8 dimensions to 11. And we therefore need to get the code to a point where we can use these standard, like other methods, like MCMC or similar. So I think that's the next task. But yes, this new Chime sample will be great, but I think only once I do my homework and get things going more efficiently.
I see. Thank you so much. Another quick question. So you mentioned that you were kind of talked about the Hubble H naught, but I think the IGN fraction is also kind of a degenerated parameter. So maybe a kind of combination between these two would be more reasonable, in my opinion.
No, completely agree. So the slide that I brushed over with about 10 seconds that was calling for people interested in this emphasised that, yes, the ionised fraction, the fraction of matter. Ionised fraction we know pretty well, we think we do. But yes, the fraction of matter in the IGM is pretty complicated. There's been a couple of papers out proposing ways to probe this. In particular, if you can study, let's say, dispersion measure around nearby galaxies and clusters and so on, and I think that's a way forward, but yes, it's really important, I agree, and come and help me, let's discuss further.
Thanks.
Sorry.
Okay, thank you very much for discussion. I think we already started this kind of. Okay, please go ahead, Jim.
Can I just add?
Sorry, we have to use the microphone, so wait a moment.
I just wanted to add a little bit about the FGM. That if you wait until Friday, you'll see that there are ways to constrain this parameter, and which might help in the future to put a tighter constraint on H0 using FRBs.
Wonderful. Can the speaker please say their name, because I don't recognise the voice?
It was a Hurricane.
Okay, wonderful. Let's talk more. I'm looking forward to Friday.
Thanks.
Okay, thank you very much for the discussion. So I think we finish the questions, but in terms of discussions, maybe we already started. But let me propose 2 possible topics. Any topics is okay, but from my point of view, in this session we had very important researches about multiple different approaches to constraining FRB progenitors. For example, as Clancy presented, FRB population analysis can constrain FRB origins. Also, empirical correlation presented by Songjin, and also classification, I believe is important to identify FRB origins too. So these things are, I think, observation is slightly different from direct identification of FRB progenitors, I believe. In the morning session, we discussed that nearby universe is more important to really directly identify progenitors. But in terms of population analysis or classifications or empirical correlation, or sorry, also I forgot to mention host galaxies, these things, if we focus on these different approaches to constraining FRB progenitors, observational strategy could be different, I believe. So therefore, I really just wanted to point out these things. And then maybe personally, again, I want to ask Clancy about FRB populations, for example. So I really personally like this FRB population analysis to constrain FRB origins. But in terms of sample, so what kind of observation would be helpful for future to get more accuracy for your analysis?
Okay, so that's an interesting question. So, firstly, I think observations that cover a broader range of parameters. So it's a classic case, right, when you're doing first year physics, where if you're trying to fit a line through a few points, you've got this classic first year physics case where you've got an x-axis, a y-axis, a few points, and you want to fit a line, right? You're learning about linear regression. If all those points are clustered about the same point on the x-axis, then you get large uncertainty in the fit.
Yes.
And if those points are spread out over a wide range, you get more constraints. So I think having experiments that cover wide frequency ranges, because as we know, for instance, FAST covers the chime frequency range. Why do I say that? It goes so far back in redshift that, other way around, so chime covers the FAST range, by the time chime goes back to higher frequencies, in the distant universe. I was thinking of FAST because it's very sensitive.
Yes.
So I think that would, having some way to get localized FRBs, and that's the key point here, you really want localizations. The statistical value of chime's DM only sample for fitting is about the same as half a dozen localized FRBs. I mean, it's good, but you really want localized FRBs. So chime outriggers, if we could get 3 fast telescopes at large distances, all observing the same sky simultaneously, that would be wonderful.
Oh, thank you very much for your comments. In that sense, I guess probably wide redshift distribution for sample will be also important factor, I guess. In this sense, the host galaxy at redshift 1 was really, to me, it's really hopeful. I mean, that was a big discovery. So therefore, I think wide coverage of the parameter spaces is, as you mentioned, is really important. Then, including, I believe, the redshift range too. So in that sense, probably not only focus on local universe, but also detecting FRBs at a distant universe will be also useful for you to constrain populations, I think.
Yeah, there's another kind of approach, I think, which is when you look at these models of dispersion measure as a function of redshift, that's the equivalent of taking a cosmological simulation, throwing 2 darts at it, and measuring, the distance between them. But of course, we know that FRBs don't occur in random places in the universe. And what's more, as soon as we localize an FRB, we know if that FRB occurred in a cluster or if it went through galaxy, halos of galaxies along the line of sight. So I think each fast radio burst localization, at the moment we're just using DM and Z. I think if we extend this to a much more detailed sample, more detailed parameters where we can use how many halos it may or may not have gone through, and more detail from the simulation, that will give us more information per FRB.
Right, thank you very much for your comments. So, any other comments or questions or discussion matters from audience? How about online people? Maybe no. Okay, so because this session was quite long, so therefore maybe people started to get tired. So maybe I think it's good time to finish this afternoon session. let's thank all the speakers again and participants.
Thank you
very
to
much.
organisers.
Thank you very much. Thank you very much for your participation. And then we finished all the session, talks today. And then today we will going to start from 9 a.m. if I remember. So yes. Therefore, for the speakers tomorrow, please access to the WebEx a little bit earlier than your talk. So then see you tomorrow morning in Taiwan time. Thank you very much. Okay, and then this is for on-site people. I don't have specific announcement, but the conference doesn't serve dinner for today, so therefore please enjoy dinner in Taichung, in Taiwan. So maybe it's easy to find restaurants in Taichung City. If you go to the Taichung train station, there are so many options there, so therefore it will be easiest way.